This is exercise 8.5, Q2. Comes from page 338 in the text. In this section, we're dealing with quantifier exchange, which is the only substitution rule for quantifiers, and it's about how to deal with negations. And also, in this section, he talks about how to do things like subderivations with predicate logic. So I'll go through and do the odd numbered ones, or as many of them as I can get through in 15 minutes, and the even numbered ones are assigned for homework. Okay, so number one, we've got a premise, it's a disjunction. We've got this universal premise, and our conclusion is this existential. But what's important to start recognizing now is equivalence, right? So the quantifier exchange rule says you can move the negation from one side of a quantifier to the other and change the quantifier, all right? So if you do the quantifier exchange rule on premise 2 here, you get the negation, you get the existential quantifier, fx, right? So that's QE2. So the negation jumps over the quantifier and it changes from universal to existential. All right. So why do we want to do that? Well, because now we have the negation of one of the disjuncts up here. And if we have the negation of one of the disjuncts, we can apply the disjunction elimination rule. And that gives us the other disjunct. So that gives us negation of, negation of universal OX, right? So in other words, we have a disjunction here, P or Q. Line 3 is not Q, so that gives us P. And again, that's disjunction elimination of 1 and 3. So all the old rules still apply the same way, right? If you have a disjunction and the negation of one of the disjuncts, you can get the other disjunct. Now this we can see is similar to our conclusion, but again, we need to change the universal to an existential, and we can do that if we just jump the negation over. So we get our conclusion on the next line, and that's by QE of 4. So that's how the quantifier exchange rule works. You move the negation from one side of the quantifier to the other, and again, you notice you can go either way. You can go from inside back to outside, or you can go from outside to inside. But when you do that, when you move that negation, you have to change the quantifier, either from universal to existential, like we did here, from 2 to 3, or, well, I guess we did universal to existential in both cases, all right? So you got to start paying attention then in these exercises to what's the equivalent of what we're trying to get, and can we get that, and then use the quantifier exchange rule to get our conclusion. Okay, number 3, we've got conditional, conditional, conditional. Now remember, you cannot apply the quantifier inference rules unless the quantifier is the main operator. And the only way the quantifier is the main operator if it comes first and there's no other operators outside of parentheses, right? So here, for example, the universal quantifier is the main operator. But here it's not because there's a negation in front of it. I mean, plus there's this disjunction here too, right? So in neither of these premises are either of the quantifiers the main operator, the conditional is. So we can't apply any of the quantifier inference rules to these premises. But since our conclusion is a conditional, what we can do is do a conditional introduction, right? So we assume KA and want LA. And again, we do this the exact same way. We indent, we assume the antecedent of the conditional we're trying to derive, and we want the consequent. So that means we're finished with the subderivation when we get to LA. Now that we have K, we can get sum x kx, where the And we get that by the existential introduction from 3. So if A is a K, we know that there exists at least one thing that's a K. So now sum x kx is the antecedent of this conditional, so we can get the consequent by conditional elimination of 1, 4. Now that's the antecedent of this other conditional, so we can do another conditional elimination to get that conditional elimination of 2, 5. So what we want is LA, so we can now get LA by universal elimination of 6. And that finishes our subderivation because that's what we wanted. So we go back to our original scope line, Ka then La, and that's by conditional introduction 3 through 7. So again, the conditional introduction as well as the negation rules that involve subderivations work exactly the same as in propositional logic. Okay, number 5. We've got some quantifiers. Now this one we can apply the quantifier inference rule to because the universal quantifier here is the main operator. This one we cannot because it has a negation in front of it. But we can apply the quantifier exchange rule to change that into that. That's QE1. So again, we just jumped the negation over, we changed universal to existential, and kept everything else the same. Now we can do, now the existential quantifier here is the main quantifier because it's out to the front and there's no other, nothing else to the left of it, and there's no other operators. Well, the negation's outside of parentheses, but that doesn't count. There's no other operators outside of parentheses. So now we can do not EA or NA by existential elimination of 3. We can do the De Morgan's there to get not EA and not NA. That's De Morgan's of 4. And we can get the double negation of 5. All right. Now, if you look what we need Z and we need not N. We can get not N easily by conjunction elimination of 6. To get Z, where is Z here? There it is. So we need to do this EA then ZA by universal elimination of 2. And we need to get EA by itself by conjunction elimination of 6. Now we get ZA by conditional elimination of 8 and 9. Okay, so we need to put those two together. So ZA conjunction not NA, that's conjunction introduction of 7 and 10. And then our last step can be that our conclusion ZX and not NX by existential introduction of 11. So again, we did the quantifier exchange first and the existential elimination. Now again, it's important we did that first because if we would have done this universal elimination first, then we would have had EA conditional ZA, And when we went to do this existential elimination, we would have had to pick new letters. We would have had to do EB or NB. So always remember from the last video, you always do the existential eliminations before universal eliminations, because existential eliminations, you have to choose a new letter, whereas universal eliminations, you can choose any letter. Okay, number 7. Let's see. So we've got an existential here, so we'll do that one first. SA and MA. Existential elimination of 2. Now we can do this conditional exchange. So again, we jumped the negation over the quantifier, changed it from existential to universal, kept everything else the same. Now we can get not MA and PA by universal elimination of 4. Not MA or not PA by De Morgan's 5. Okay, we need SA, so we can get that by conjunction elimination of 3. And then we need not PA. Well, here's not PA, and it's in a disjunction. So let's get MA by conjunction elimination of 3. And we do not MA by double negation of 8. And then we can do this disjunction elimination to get not PA. So that's disjunction elimination of 6 and 9. Now you do have to do this double negation, because to do disjunction elimination you need a disjunction and the negation of one of the disjuncts. But MA by itself is not a negation of anything. There's no negation. So you have to do this double negation first, then you can do the disjunction elimination. Okay, so now we put SA and not PA together with conjunction introduction of 7 and 10. And then our last step is the existential introduction of 11. Okay, one more, 9. I'll try to do this one quick, although it's a long one. So it's a biconditional. So we can do biconditionals by doing 2 conditional introductions. So we start with WTX want some x CX. With WTX we can get some x FX and CX by conditional elimination of 1 and 3. We got a biconditional. We got one of the sides of the biconditional that tells us we can get the other side with biconditional elimination. Now we can do FA and CA by existential elimination of 4. And we can get CA by junction elimination of 5. And then 7 we can get some x CX by existential introduction of 6. And that was what we wanted. So our first subderivation is over all x tx conditional some x cx by conditional introduction 3 through 7. Okay, since the biconditional, we have to get the other one too. So we indent again. This time we assume some x cx want all x tx. But since I'm running out of time, I'll just explain. So now you do again, you'd get C, well, use CB since we already used A. Then you do this CB, oops, CB, then FB by universal elimination. Then you get FB by conditional elimination. And what do we want? All x tx. Let's see. All x tx. So we get FB Um,